All right, everybody, in this first video, we are going to start chapter R, which is kind of like the review material for this course. So as I go through the next two videos and do chapter R for you, if this stuff looks pretty familiar, that's great. But if not, this is a chance for everybody to kind of get on the same page before we can jump into chapter 1 and I believe video number 3. So in section R.3, we are going to talk about the laws of exponents and then kind of go over a review of radicals because we will see a lot of those throughout this course. So just a couple of rules. Like I said, I'm not going to spend a lot of time on this slide, but if you need to pause the video just and write them down, that's fine. But let's suppose that you have an m and an n that are both positive integers, and we know that a and b are real numbers. So these are just some of the rules that you need to remember about exponents. So let me kind of just run through these for you. So number one, if you have a b to the m times a b to the n, and they have the same base, you can put them together by adding the exponents together, so m plus n, versus if you are dividing them, so b to the m over b to the n, you would subtract them, the top always the top minus the bottom, so m minus n. Where I see a lot of people mess up on stuff like this is mixing up rule number 1 and rule number 3. So notice that rule number 3 says if you only have one base b raised to an m and then that whole thing is raised to another power, that is when you multiply them. In the first one there were two bases, so we added them together. Rule number 4 says that if you have two terms being multiplied together, such as a times b, and that whole thing is raised to a power n, then you can apply the n to both terms as long as it's just multiplication on the n side. Same thing with division. So if you are dividing an a over b and all of that is raised to a power of n, you can raise the nth power to both terms. Notice this only works for multiplication and division. It does not work for addition or subtraction. And we'll see why a little bit later. You probably have seen before that if you ever raise something to the 0 power, it is not 0. Instead, that is a power of 1. So you're going to get 1 as an answer. And then if you have just a regular base being raised to a negative exponent, you can flip that over and write it as a reciprocal as 1 over b raised to a positive power of m. So let's do some examples with some of those properties, and I'll kind of explain each property along the way as we do these, but hopefully most of this stuff looks pretty familiar. So for example, number 1, it says, what if you have a negative 3x all being raised to the 0 power? Well, since the entire thing is being raised to the 0, one of your properties says that that does have to equal 1. Now, the difference, as you probably are guessing, between number 1 and number 2 is a slight difference in parentheses. So be careful on number 2 where it says negative 5 to the 0. Since this negative is technically not grouped with the 5 using a parentheses like number 1 was, we can't assume that. You can only apply the 0 power to the 5. So this part right here becomes 1, and then this negative comes down, and you get an answer of negative 1. Just a small difference there, and that's going to apply to any power technically, but I wanted to show you with the zeros first to kind of get you thinking that way. Number 3, you've got negative 4 times x cubed times y to the 7th all being raised to the squared. So what you can do is, since all of this is multiplication, you can apply this squared power to every term inside of the parentheses. So this would be negative 4 squared times x cubed all squared times y to the 7th all squared. And then just do each one individually. Negative 4 squared is 16. X cubed all squared, since it's one base, so there's only one x, you multiply them together, so that's x to the 6th. And same thing with y, 7 times 2 is 14. So therefore this becomes 16 x to the 6th y raised to the 14th power. All right, let's do some more. So number 4, what if you have 7x to the 4th y cubed times negative 3x to the 5th y squared? So you're multiplying two separate things together. That's fine. Just combine what you can and keep together what's similar. So as you can see, if I do one step at a time, number 1, I'm going to multiply the numbers together. 7 times negative 3 is negative 21. x to the fourth times x to the fifth. Since there are two different x's, so they both have separate bases, you have to add the exponents. So 4 plus 5 gives you a 9. And then same thing with the y's. You have a y cubed times a y squared. So if you add the exponents together, this becomes y to the fifth. Your final answer is negative 21 x to the ninth y to the fifth. Number 5 is an example of division. So we've got 42x cubed y to the 5th over negative 35 x to the 8th y to the negative 7th. So if I simplify this one, now this one simplifies a little bit differently because you've got to deal with the fractions here. So let's start with our constants again. You have a 42 divided by a 35, with a negative 35, sorry. They both have a 7 in common. So if I were to divide both of these by 7, the 42 would become a 6 and the 35 would become a 5. So your first step I notice is that when I have my fraction, there's a 6 on top and a negative 5 on the bottom. On your x's, you have an x to the x cubed divided by x to the 8th. The rule of thumb here is that you always just pick on the bigger power. It's a little trick there. So since 8 is bigger than 3, I know that the x is going to be on the bottom, and you subtract largest minus smallest. 8 minus 3 is going to give you a 5 on the bottom. As far as the y's go, be careful because 5 is bigger than negative 7. So if I put my y on top and I subtract, now if you need to write this out, your biggest number, which is 5, minus your smallest number, which is negative 7, that does become addition, and 5 plus 12 is 17. So your final answer is 6y to the 17th over negative 5x to the positive 5th. Sorry for that little stray mark. That's not a negative. All right, and then probably the most confusing one here, we have a lot of stuff going on. So what about number 6? You've got r squared v to the 7th, k to the negative 4th, over r to the negative 4th, v to the negative 6, k to the 7th. So this is kind of combining a few different rules here. First thing I'm going to do is that since everything in here is either multiplied or divided, that's the key here. You can take this negative 3 and you can multiply it by every single power inside of this. Once again, you can do that because everything is everything is multiplication or division. So if I multiply all the powers by negative 3, you should get an r to the negative 6, a v to the negative 21, a k to the 12 over r to the 12th, v to the 18th, and k to the negative 21. Sorry for my bad handwriting there. That's an 18. Then it looks just like number 5, where you're looking for the highest powers in this case. Now, if you notice, all of the highest powers are actually on the bottom this time. So in the end, since none of these will be on top, I can put an understood 1 there. And then you're subtracting the numbers on the bottom because they are bigger minus the smaller numbers on top. So let's go one by one, starting with r. 12 minus a negative 6 is 18. For v, 18 minus a negative 21 is 39. And on k, the only two double positives, 21 minus 12 is going to give you k to the 9th. And that is your final answer. Now on that last one, you didn't have to go in the order that I did. I just chose that's the way that I first recognized it. So you could have easily simplified the inside of your parentheses first and then applied your negative 3. That's completely up to you in this case. Either way is fine. All right, so kind of running through some radical ideas. Once again, if you need to pause the video to write this down, that's fine. But essentially it says that for any integer n that's bigger than or equal to 2, we can define the nth root of a number b as the following. So whenever time you write a root, remember that you take the nth root of b is equal to a if and only if a to the n equals b, which means that you could raise n to both sides in this case. Now, remember that if n does equal 2, it is understood. So anytime you want to write a square root or a second root, you'll see that we won't write the 2, but any number bigger than 2 you need to write. You'll see that a lot. Reading through some of the other stuff. So if you are taking an nth root of a to the n, keep in mind that if n is odd, you could get negative answers, versus if n is even, you cannot get negative answers, which is why you see this absolute value right here. Some of the same rules of exponents also apply to radicals. So if you remember that if you are multiplying two radicals together, such as a to the b, the square root of a and the square root of b, since they're both the same root, so they're both square roots, you can put those together as the square root of a times b. And then similar with division. If you have a square root of a divided by a square root of b, as long as both the roots are the same, you can put those together and you can do the square root of a divided by b. So let's look at some examples. Now, some of these square roots are going to come out to really nice answers, some of them will not, and we'll talk about how to break down the ones that are not nice answers. Now, the first two we have here are actually pretty nice. What is the square root of 144? Well, hopefully you recall from, you're asking yourself, what number squared is 144? That's going to be 12. This can also be done with letters. So for example, number 8 says, what is the square root of 64z squared? Technically, since both of these numbers are being multiplied, you can do them both separately. So the square root of 64 is 8, and then the square root of z squared, the square root, remember, is an understood 2 root. This 2 root goes into this 2 root one time. So essentially you're doing 2 divided by 2 is 1, which is why you have a z to the first power. This idea right here will play a role a little bit later. What happens when it doesn't come out to be a whole number? We'll talk about what to do there. And then our first example of what's not a perfect square root. So what is the square root of 150? So if you maybe remember that anytime you have a square root that's not a perfect number, we do things like factor trees. And I'm going to show you, or remind you what that is. Essentially, you take the number, which is 150, and you break it down into numbers that are nice. So what does 150 break down into? First thing I think of is 15 times 10. And then I know that 15 is 3 times 5. And 10 is 2 times 5. Now breaking them down to times 1 is not helpful. So once you get to a bunch of numbers that are very small and don't break down anymore, just stop. You're looking for any pairs. So in this case, I see a pair of 5s. And the reason I say pairs is because you're doing a square root. The root tells you how many like terms you need. Whichever term you have a pair of, that is the number that comes outside of the square root. So both of those 5s combine into one 5, and that comes out front. The other two numbers, the 3 and the 2 that are left over, you put them back inside and you multiply them together. So you will end up with 5 square roots of 6. All right, so going on to the next slide. Let's do a couple more. What about the cube root of 48x to the 5th for number 10? So first thing I'm going to do again is I'm going to start with my 48 and I'm going to break it down. So 48 breaks down into, let's see, that's 12 times 4. The 12 breaks down into 4 times 3, and the 4 breaks down into 2 times 2. This 4 also breaks down into 2 times 2. Now you will notice that you have a cube root this time, so you're not looking for pairs, you're looking for threes. So 1, 2, 3. Those 3 2's right there can go together outside of the cube root. Now inside of the cube root, you multiply the two numbers remaining, so 3 times 2 gives you a 6. As far as the x goes, here's the problem. 5 divided by 3, so you take the power of x, divide it by 3. That is not a nice number. Instead, this goes, so 3 goes into 5 one time with a remainder of 2. The number of times that it does go in is how many you can bring out. So I can bring out 1x, and then the remainder is the power that's left on the inside. So that would be x squared. So this is 2x times the cube root of 6x squared. All right, so number 11. What is the square root of 50 x to the 5th y cubed? So just more letters here, but it doesn't change the process. You're going to take the 50 That breaks down into 25 times 2, which breaks down into 5 times 5, and that's a 2. You're doing a square root, so you're only looking for 2 of a certain number, which we got pretty easily there. That means a 5 can come out front, and inside of the square root, you have a 2. If you take the power of x, which is 5, divide it by the root, which is 2, 2 goes into 5 2 times with a remainder of 1. That means you can bring an x squared out front, and you can leave an x to the first on the inside. For the y, if you take the power of 3 divided by 2, that goes in with a 1 remainder 1, so that means that 1y comes out front and 1y stays on the inside. Your final answer is 5x squared y times the square root of 2xy. All right, so now for the first time, what happens if you want to simplify numbers raised to fractions? So write negative exponents as positive and then assume variables represent positive real numbers. So here's the nice thing is that little writing over here, we saw a little bit earlier that we defined roots as having an nth root of a raised to an m. Well, let me rewrite this. So I'm actually going to cross that out. That's kind of how it was found. I'm actually going to define the root as r, and I'm going to define the power as p. It's just a little bit easier to learn this way. What we know about roots is that they are equivalent to the base, which is a, of power over root. Now you can go either direction in this equation. As you can see on all 3 of our examples, they're all given in the second form. So we're going to transform all of them back into radical notation. So on the first one, when it says 49 to the 1/2, you're going to go ahead and put your radical there. The 49, the base always goes inside. The number on top is your power. It's the power of 49. And the number on the bottom is your root. So this is essentially asking you what is the square root of 49, which is 7. All right, same idea with this one. You have a negative 9 to the 1/2. Now, since we don't know, since there's no parentheses here, you cannot apply the 1/2 to the 9, and the negative, only the 9. So I'm going to leave the negative there, and it looks just like the first one. It would be a square root of 9 to the first. Now we should know that the square root of 9 is 3, but you do have a negative out front, which is negative 3. But what happens when you have a negative power? One of the properties I showed you a little bit earlier today is that if you have a negative exponent, you can use the reciprocal rule and rewrite this as 1 over 8 raised to the positive 2/3 instead. And then same idea. You would have a 1 over, I'm going to put my radical in my base. The top number is your power, which is 2. The bottom number is your root, which is 3. This would be 1 over the cube root. 8 squared is 64. And then actually the cube root of 64 is a nice number because you ask yourself what number multiplied by itself 3 times is 64. That would just be 4. So your final answer on number 14 is 1/4. But the big thing to note is make sure you know this relationship between exponents and radicals. All right, and then one more problem here. Just kind of showing you the same idea again with these exponents. So it says write negative exponents as positive, assume variables represent positive real numbers. Now sometimes you can't simplify every single one. So example like on number 15 when it says x to the negative 1/4, on your homework all they want you to do is to practice the property that when you have negative exponents, you can flip them over and write it as 1 over x to the 1/4 power. On number 16, you can also use your properties even if there are fraction exponents. So if you have something like x to the negative 3/5 times x to the 8/5, since they both have bases of x, you can put these together by adding their exponents together. So you can add the negative 3/5 and the 8/5, which will give you x to the 5/5, and 5 divided by 5 is 1. So you can either write it as x to the first, but usually you don't write that first power. So your answer there is x. On number 17, you see that 1/2 power again being raised to everything. We talked about on the last slide that a 1/2 is the same thing as a square root. We're going to see that a whole lot, so that's something that I would definitely note for yourself. So I can rewrite this as the square root of 9x squared y cubed. Now the good news with this one is that the square root of 9 is a perfect number. So you have your 3. Now there may be some stuff left over on the inside of the square root, so I'll go ahead and put it there. Let's check. Your x squared, if you take the power of 2, and remember it's an understood root 2, divided by the root, that gives you a perfect 1. So therefore there are no x's left over on the inside. All of your x's come out as a power of 1. Versus the y, which has a power of 3 divided by 2, which is 1 remainder 1. So therefore you can bring 1y out front and there is 1y left over on the inside. So your final answer is 3xy times the square root of y. All right, so that ends section R.3. We're going to go ahead and move into R.4, our second of 5 review sections. So this is probably the shortest of the review sections. It's a review on just what polynomials are and then what are some few properties that we can do with those along the way. All right, so it says perform the indicated operations and write answers in standard form. So just once again, a polynomial is just a list of terms including numbers, x's, x squareds, x cubes, blah, blah, blah. Your job is to be able to put them together using different operations like adding, subtracting, multiplying, dividing. We're going to see all of that. So on one like this, number one, just asking you to add the two polynomials together. So when you're adding or subtracting, it's as simple as just putting your like terms together. So let's combine some like terms. And it says standard form, that means start with the highest power. So I see a negative x to the 5th and a negative 3x to the 5th. So if you put those together, negative 1 and negative 3 is negative 4x to the 5th. Then you have a positive 3x to the 4th. And a positive 1x to the 4th, which gives us a positive 4, excuse me, 4x to the 4th. There's only one cube term, so I'm actually going to circle it because it's all by itself. So that 9x cubed, it doesn't go away. It just comes down here by itself. Then you have a negative 9x squared and a negative 2x squared. So negative 9 and negative 2 becomes negative 11x squared. You only have one x term, so that's going to be your plus 8x. And then finally, I'll just squiggle the last one. You have an 11 plus an 11, which if added together does give you 22. Adding polynomials is one of the easier things to do. It doesn't require any rewriting. All you do is find your like terms and you add the constants that are in front of them. Now where you may mess up at, and I see students do it all the time, is when you are subtracting polynomials. So let's make sure we review that. Remember, what do you have to do when you have a negative in front of a parentheses? You have to take this negative and you have to distribute it to all three of these terms. So that's going to end up being, if I rewrite the problem, 3x squared minus 3x plus 3 minus a 5x squared plus a 7x minus 4. And then just like the one above, you can add your like terms together. So you have a 3x squared and a minus 5x squared, which is minus 2x squared. You have a negative 3x and a positive 7. So negative 3 plus 7 is positive 4x. And then a positive 3 and a minus 4 gives you a minus 1. That is your combined terms. Just make sure you remember to distribute the negative to all three of those terms. All right, so multiplying. There's many different ways to be multiplying, and maybe you're thinking of a shortcut. We're going to get to that shortcut in a second, but it only works on certain problems. In general, when you want to multiply two polynomials together, we're going to use what we call the distribution property. So, for example, on number 3, when you've got 4x squared times negative 3x squared plus 5x plus 8, I'm going to take this 4x squared and I'm going to distribute it to all three of those terms. When I do that, 4 times negative 3 is negative 12. X squared times x squared is x to the 4th. 4 times 5 is 20. X squared times x is x cubed. And then 4 times 8 is 32, and you have the lonely x squared to go along with it. And that's it. You just distribute your term through to all the other terms in the other polynomial. Now, where you got to be careful is what if both polynomials have more than one term? Well, that just means you're going to have to probably distribute more than once. So let's do this one step at a time. What if you have something like x plus 2 times 4x cubed minus x plus 6? First thing I'm going to do is I'm going to take just the x and multiply the x by everything. I'm going to do this part in red. So if I multiply everything on the right by an x, you should get a 4x to the 4th, a minus x squared, and a plus 6x. And then if I come back, and I'll change to green here just so you can follow along, I'm going to take 2 and multiply it by everything as well. So that would be a plus 8x cubed minus 2x plus 12. And then you can put all of your terms together. So there's only one x to the 4th term, so that's 4x to the 4th. Actually, oh well, no, a couple things. You have a plus 8x cubed, a minus x squared, and the only terms that go together are your x terms. So 6x minus 2x is 4x with a plus 12. That is another example of the distribution property of multiplying polynomials. So here's probably a shortcut you've seen before, and it's the idea of foiling polynomials. Now, this only works if both polynomials only have 2 terms. So what you may remember about FOIL is that it represents the analogy for first, outer, inner, and last. It's just a way that you can end up multiply them together. It's just a shortcut way, but essentially that's just the same thing as distributing. So if you want to always just distribute, that's fine, but I know some of y'all remember the technique of FOIL, so I'll show you the FOIL technique as we do this. So let me kind of write out a lot of stuff on the first one. You've got x plus 7 times x minus 5. So if you do your FOIL technique, the first thing you do is you multiply your first terms. So your f would be x times x, which is x squared. Your outer, so you multiply the 2 outer terms together. X times negative 5 is negative 5x. Inner is the 2 inner terms. So 7 times x is 7x. And then finally, the last is just multiply the last terms together. 7 times negative 5 is negative 35. I see that there are 2 x's to put together here, so negative 5x plus a 7x is plus 2x, so I'll go ahead and put that together. That is your answer. But it's the same thing as distributing. That's really up to you how you would do that, but either way is fine by me. So what about number 6, 5x plus 3 times x plus 7? So if I do my FOIL technique again, you're going to end up with first is 5x times x, which is 5x squared. Your outer, 5x times 7, is 35x. Your inner, 3 times x, is 3x. And last, 3 times 7 is 21. Once again, you can combine the 2 x terms that you have, and you should get a final answer of 5x squared plus 38x plus 21. And that is your final answer there. So that's just an example of using the FOIL technique. I know some of y'all have seen it before, but if you've never seen it, there's an example. Remember, it only works, though, if both polynomials only have 2 terms in them. Now, there are some special products. Over the years of teaching this class, I have seen some kids love these rules and some kids just don't use them at all. It's really up to you, but I figure I would show them to you. That way you know what they are. So it says, let A and B represent any real number or algebraic expression. Then there are 2 different ways, there's 2 different techniques here. Probably the most important one, and this is one that I'll use a little bit more in the next video. It's called the difference of 2 squares. So of everything on this slide, this is probably the most important here. The difference of two squares says that if you are multiplying two polynomials together, and the only difference is that one is addition and one is subtraction, there is a shortcut to this. If you were to multiply, let's say, a plus b and a minus b, you would normally think of FOIL. But if you try to do the FOIL technique, you'll notice that your outer and inner terms cancel. Now, if you want to do that every time, that's fine. There's nothing wrong with showing that step. But you may want to learn the shortcut because it may help you in the next video, is that when you multiply two difference of squares, you can essentially just, where's a different color? You can just square both of your terms, so a squared and b squared, and then subtract them on the inside. There's also two other properties down here at the bottom. These are just shortcut ways of squaring binomials. I'll be honest with you that I don't use these very often, because what I usually do is if I have something like a plus b squared, I'm probably just going to rewrite it as a plus b times a plus b, and I'm going to do the FOIL technique. I just prefer to do that because there's already other stuff you're going to have to memorize along the way. This is just one less thing you don't have to worry about. But if you want to learn them, they're right there. Those are shortcuts, but that's up to you if you want to learn them. So let's do some examples. It says use the special product formulas to find each product. Now the one I am going to use is that difference of squares because it does help a lot going forward. So number 7 is an example of that. You have 5x minus 3 times 5x plus 3. Normally you would do FOIL here, but if you remember, the difference of squares says that since both of these are the same, except one is subtraction and one is addition, you can simply take both terms, so the 5x and the 3, you can square them and just subtract them. So if you square both of those, it will be 25x squared minus 9. And that's it. That's going to save a lot of time. Now, if you chose to go ahead and just FOIL that, and then you'll see that some terms cancel, that's fine. Nothing wrong with that either. Number 8 and number 9, if you want to use those shortcuts I showed you, that's fine. But in all honesty, for example, number 8, when I see something like x plus 6 all squared, I'm usually just going to spend the few extra seconds because I don't use those other rules that often. I'm going to rewrite this as x plus 6 times x plus 6, and I'm going to do my FOIL technique. So that would be your first. So x times x is x squared. Your outer terms multiplied is going to give you 6x. Your inner terms multiplied are going to give you 6x. And your last terms, the 6 times 6 is 36. And then you can combine those two terms in the middle, which is going to be x squared plus 12x plus 36. That is your final answer. I do the exact same thing when it's subtraction, so no difference. When I see something like 2x minus 5 all squared, I just rewrite it. And this is equivalent to 2x minus 5 times 2x minus 5. And then I'm going to do my FOIL technique again. So first, 2x times 2x is 4x squared. Your outer multiplied together gives you a minus 10x. Your inner multiplied together gives you a minus 10x. And your last, the negative 5 times negative 5, is positive 25. Put those two x terms together, and you should get 4x squared minus 20x plus 25. That is your final answer for number 9. So I use the first shortcut a lot, and we'll do it a lot more in the next video as well. Those second two, like I say, it didn't take that long just to rewrite them and do your FOIL technique. All right, and last but not least, like I said, that's a short section. And then another short section is just operations with radicals. So we talked about radicals a little bit earlier in section R3. So what are some certain operations like multiplying, adding, subtracting, all that stuff? How do we apply that when it comes to radicals? So not really anything new here. I'm going to kind of do this by examples. I think it makes a lot more sense. But the instructions say simplify the following radicals and then put them together assuming all variables represent positive real numbers. So on number 1, you have the square root of 20x minus the square root of 45x. The only way that you can put two radicals together is if the insides of the radicals are exactly the same thing. While they both do have an x, and that's good, we're not going to mess with those, they both have different numbers, so we cannot combine these yet. So the first thing I'm going to do is, since the x's are already good, I'm going to leave those alone. I'm going to instead break down 20 and 45 using those factor trees from earlier to see what they simplify into. Well, 20 breaks down into 4 times 5. The 4 breaks down into 2 times 2, and the 5 doesn't do anything. So you have a pair of 2's because of the square root. So I can bring the 2 out front, and that 5 I can leave left over inside with the x. All right, minus 45 breaks down into 9 times 5. 49 is 3 times 3 with the 5 coming down. This one you have a pair of 3's that you can bring out front, and once again you can leave that leftover 5 inside with the x. As you can see, our radicals match exactly now. Since they match exactly, they don't change. Instead, you combine the numbers that are in front of them. So this 2 minus this 3 makes it a -1 times the square root of 5x. Now the 1 is not really necessary. If you want to write it, you can, but we can write our final answer as the negative square root of 5x. All right, so I showed you one. Let's do another example, same idea. Number 2 says you have 2 times the square root of 75x plus 5 times the square root of 3x. Once again, the x's match on the inside, but the numbers do not. So I need to see if I can break down the 75 and the 3. So let's see, 75 does break down into 25 times 3, and then 25 is 5 times 5. So there's your pair of 5's. The difference is that since there is already a 2 out front, that cannot go away. When you write this, you have to leave the 2 there, you bring the 5 out, and then that 3 stays on the inside with the x. Well, as you probably have noticed if you're working a little faster than I am, is that the 3 doesn't break down. That means you can't break down the second one at all. It's going to have to remain as 5 times the square root of 3x. But that's okay. Your roots match, so you can actually put these together. This would be 10 times the square root of 3x plus 5 times the square root of 3x, and then you add the two numbers in the front, and you should get an answer of 15 times the square root of 3x. And there you go. So if you want to add or subtract radicals from each other, you have to make sure that their radicals match exactly. Multiplying is no different. So when you multiply radicals together, you're going to use the same properties we talked about in previous sections. So for example, number 3 is asking you to take the square root of 7 and multiply it by 3x plus the square root of 5. So what I'm going to do is I'm going to take this square root of 7 and I'm going to distribute it to both terms inside of the parentheses. Root 7 times 3, since they're both not the same, one's a root and one's a number, they don't go together. All they do is they sit next to each other as 3 times root 7 with the x. But since the root 7 and the root 5 are both square roots, you can put those together as one big square root and just multiply the insides. 7 times 5 is going to give you 35. And that is your final answer. That property I told you earlier, the difference of squares, like I said, it shows up a lot of the time, and here it shows up again. You've got the square root of x plus 3 times the square root of x minus 3. Since the only difference is the expression inside, you can shortcut this. Now, once again, if you want to FOIL it, that's fine. But the difference of squares says that I'm allowed to take the first term, which is root x, and square it, take the second number, which is 3, square it, and subtract them from one another. Now, if you simplify this, the square root of x times the square root of x, since this is a power of 2 and this is a root of 2, they actually cancel each other to just give you an x. and then 3 times 3 is 9. So that simplifies just into x minus 9. All right, another problem we're going to run into from time to time is that when we're solving problems, we're going to end up with square roots on the bottom, and that's not a good thing to have. We cannot have a square root on the bottom. So when we do, we're going to do the property that's called rationalizing the denominator. The easiest way to do that, and really well, not the only way, the easiest way is ones like this. When you have just a singular square root on the bottom, such as 1 over the square root of 5, the only way that you can get rid of this is, as we saw on the last one with the root x's, if you multiply the bottom by square root of 5, I know the square roots will go away. But whatever you do to the bottom, you have to also do to the top because that has to keep it equivalent. Then you can multiply straight across the top and the bottom. 1 times the square root of 5 is the square root of 5, and the square root of 5 times the square root of 5 is just 5. As you can see, it's not a different answer. It looks completely different, but these are equivalent, but there are no radicals on the bottom. That's the key there. It's no different if you have multiple radicals to deal with. So what about root 3 over root 7? That root 3 on top, I'm not worried about. It's not causing a problem. It's the root 7. So if I want to get rid of the root 7, I'm going to multiply the bottom by root 7. But I have to also multiply the top by the same thing, or I'm changing the problem. Multiply straight across the top and the bottom. The bottom's the easy part. Root 7 times root 7, like we wanted, just becomes a 7. And on the top, root 3 times root 7. Since they're both roots, you can multiply the numbers and leave them on the inside. 3 times 7 is 21. So you get a rationalized denominator of the square root of 21 divided by 7. And last but not least, to finish up this first video and finish up section R5, what happens when you have not only a radical on the bottom, but another constant either being added or subtracted? These take a little bit more work. It's not overly difficult, but you got to do a few more steps to rationalize these denominators. So let's start with number 7. Let me show you what you have to do. If you have something like 7 over 8 plus the square root of 5, just multiplying the top and the bottom by root 5 is not going to help you here because you're just going to add extra roots on the bottom. So instead, when you have a root and you have another constant, we're going to do the idea, and I'll write it up here at the top. We are going to multiply by the conjugate. And what the conjugate is it plays a role in the idea earlier I talked about, the difference of squares. I'm going to take what's on the bottom, the 8 and the root 5. I am not going to change, but instead the conjugate says I can just change the sign in the middle to a minus. Now whatever you do to the bottom, you're going to have to also do it to the top, so I'll put it up there. Now let's add some parentheses here just so it's a little bit easier to picture this. On the top, all you have to do is take that 7 and distribute. So 7 times 8 is 56 minus 7 square roots of 5 all over. Now since the bottom is a difference of squares now, all you have to do is take the first term, which is 8, square it, the second number, which is root 5, square it, and subtract them. And then we're going to clean this up. This would be 56 minus 7 square roots of 5 all over 8 times 8 is 64 minus root 5 times root 5 is 5. That becomes 56 minus 7 square roots of 5 all over 64 minus 5 is 59. That is your final answer. It doesn't look as pretty. The radical is now on top though, and there are no radicals on the bottom, so therefore it is rationalized. All right, on the bottom, same idea. You've got a negative 4 divided by the square root of 3 minus 7. Your root 3 minus 7 is the problem, so if I use the idea of the conjugate again, I'm going to multiply the top and the bottom by the square root of 3, but now plus 7. That's how I can get rid of my radicals on the bottom. On the top, it's very similar. You're going to take that negative 4 and distribute it. So it would be negative 4 times the square root of 3, and negative 4 times positive 7 is negative 28. On the bottom, if I do my difference of squares rule, I can take the square root of 3 and square it. I can take the 7, square it, and subtract them. This will become negative 4 times the square root of 3 minus 28 all over root 3 times root 3 is 3, and 7 times 7 is 49. This becomes negative 4 square roots of 3 minus 28 all over a negative 46. Now, two things actually happen here, and now you can do them both at the same time, but I'm going to do them separately just so I don't lose anybody. The first thing I notice is that they are all negative numbers. Since all three terms, the 4 root 3, the 28, and the 46 are all negative, you can just get rid of all the negatives. They all end up canceling each other out. So you can write this as 4 square roots of 3 plus 28 all over 46. But now, do you notice what they all share in common? If you notice the 2, you are correct. Every single one of these numbers has a 2 in common. So what you could do is you could take a 2 out of everything. This 4 becomes a 2. If you take 2 out of 28, it becomes 14. And if you take 2 out of 46, it becomes 23. So this is going to end up giving us a 2 square root of 3 plus 14 all divided by 23. And that is your simplified rationalized denominator. So that ends section R.5. That also ends my first video here. In the next video, we will continue on. There are 2 more sections of review material we need to go over. So I will cover R6 and R7 in the next video.